Okay, so thank you, Sanjib and Abhishek, and thanks for the invitation. And yeah, this is my third time in this school, so I really enjoyed it very much. And so today I'm going to talk about random matrix theory and its certain, a number of applications. And so, exactly like what Joachim did in the first lecture, I just want to give an overview of the subject, and without going into too much details, technical details, and just to tell you why this subject is interesting and why one should study, and what are the different applications and so on, and a little bit, historical background of the random matrix theory. So, and then from later half today or maybe from tomorrow, I'll go into the blackboard only. So now before I start these slides, I just want to tell you what is random matrix theory. So what is matrix? So if you have a, let's say, n, if you don't see very well from the back, please let me know. I'll try to write as big. So imagine that you have a n by n matrix. So all of you know about matrices, right? So if I give you a matrix, you can diagonalize this matrix. So I'll denote it by X, this matrix. So if you diagonalize this matrix, you will get n eigenvalues and corresponding eigenvectors. So let's call them lambda n, right? So for any given matrix, you can always diagonalize it and get n eigenvalues. Of course, in general, these eigenvalues are complex numbers if your matrix doesn't have any special symmetry. In certain cases, if the matrix has some symmetries, then these eigenvalues can be real. Can anybody tell me when do you get real eigenvalues? Hermitian. Everybody knows quantum mechanics. Great. Okay, so you said Hermitian, but there's an even simpler one. So the complex Hermitian is one example. Real symmetric, very good. So real symmetric means that the elements of X's are real and you have the X transpose, which is equal to X. And Hermitian means that X dagger, which means you transpose and then takes complex conjugate, X dagger is X, right? So if you have such symmetries, then your eigenvalues are all real. Is there any third example? Anybody knows? Quaternion, yes, complex quaternions. But quaternion is already a complex word, so I'm not going to talk about quaternion at all. But okay, it's some generalization of complex numbers. These are called self-dual matrices, okay? So these are the three classes for which the eigenvalues are known to be real, and they are called Dyson's threefold way. Dyson is a guy who actually studied quite a lot matrices. So far I'm not telling you about random matrices at all. I'm just telling you some basic properties of matrices, right? So these are sufficient conditions. That means if your matrix is either real symmetric or complex Hermitian or complex quaternionic, you will have real eigenvalues, guaranteed. But of course, these are not necessary condition. I mean, there could be other matrices with other symmetry which may have real eigenvalues. But these three are the most well-studied cases, and they are definitely give rise to real eigenvalues. Okay, and we'll see as you already pointed out, that, because in quantum mechanics you always deal with, or Hamiltonian is always a Hermitian matrix, which means if you think of these as the energy eigenvalues, they're always real. Okay? So physicists are typically interested in these kind of complex Hermitian matrices. So quite often we deal with matrices with real eigenvalues. Okay? But in principle, you can have complex eigenvalues as well. Okay, so this is matrix. So now imagine that these elements of this matrix, they are random variables. So for example, let's take a real symmetric matrix. Let's take 2 by 2 for simples. So it has 2 eigenvalues, clearly, lambda 1, lambda 2. Now imagine that the matrix entries, so if you change the matrix entries, again you diagonalize, you get 2 different eigenvalues, right? Every time you diagonalize, you get a different set of numbers. So for each realization of such matrix gives rise to a certain number of eigenvalues. Now imagine that these entries themselves are random variables. You draw the entries from some distribution. How you draw it, that will be defined more precisely later. But let's take a simple example. Suppose I say that I draw each entry. So there are 3 independent entries, because this guy, because of real symmetric, so it's only this, okay? 3 degrees of freedom. So suppose I choose them independently, okay? So that means joint distribution of these guys, just factorize. So this is the IID distribution that Sanjib talked about this morning. So let's take something like this. Doesn't matter, whatever number, basically Gaussian. We'll see later that why I choose this factor to be 1 here and half in the other 2 cases. I'll explain that later, okay, with some normalization constant. That means, it's very easy to generate such a matrix, right? In your computer, you just choose this guy from a Gaussian distribution, this guy from a Gaussian distribution, this guy from a Gaussian distribution. For each realization of your matrix, you diagonalize, you get 2 eigenvalues. And these eigenvalues, therefore, will change from one realization of your matrix to another realization of matrix, right? So they're also random variables. So random matrix means that the entries are random variables. In general, drawn from such joint distribution, which need not factorize like this. It will factorize if they are independent, but in general, you can choose from some joint distribution of the entries. And then once you choose your matrix, then you diagonalize. You get, let's say, for the real symmetric matrix, you get n eigenvalues, which are also then random variables. So the whole, game of random matrix theory is to understand the spectral properties. That means to understand the statistics of these eigenvalues. How are these eigenvalues distributed? Okay, so spectral properties of eigenvalues given the joint distribution of the entries. Okay, so this is the sort of central problem in random matrix theory. RMT means random matrix theory. Okay. Then you can ask, many hyperfine questions like, you can ask what's the distribution of the largest eigenvalue, or what's the distribution between the gap between the eigenvalues, how many eigenvalues are there in a given interval. So many different observables you can ask. So the generic problem is this: you give me the joint distribution of the entries, and I want to find out some properties of these eigenvalues, which are also random variables. Okay? So this is the central problem. So now I want to tell you why we are interested in a little bit history about this problem. And the amazing thing is that this problem, very easy to state, but it's not always easy to solve, as we will see. And it has amazing number of applications. It goes back almost 100 years, but even today, we keep on finding new and new applications, and I'll try to explain to you why so many applications of this basic problem. Okay, so let's start with a little bit of history. When did the random matrix theory first, come about in the scientific literature? So this is, again, you remember this morning, Joachim talked about Patrick Matthew, who in 1831, was it? 1831 in Edinburgh. So I want to show you another Edinburgh connection, but this is 100 years later. Okay, so first appearance of random matrix theory was by this gentleman called John Wishart. He was a statistician at Edinburgh University. And as you see, this paper first appeared in 1928, which is about 100 years later than Patrick Matthew, and 100 years back from now. And it appeared in a biology journal, biology statistics journal called Biometrica. Okay? And he was interested he was a statistician, so he was interested in a very simple question. So what is the question? This was much before physics, okay. So this question he was interested in just can be formulated as follows. So imagine that, so a simple example, so imagine that you have a class like this, and you have, let's say 2 subjects, physics and maths, and this is, let's say you have 3 students, okay. And this is a table, 3 by 2, which is just the score of an exam, let's say. So somebody got X11 in physics, X12 in maths, student number 1. Student number 2 got X21, X22, X31, X32. So in general, it will be some M cross N rectangular matrix. Okay? Now, so the question that Wishart was interested in is that, is there, so this is in a given exam. When you look at the exam papers, you look at the scores, and he was asking himself, is there any sort of correlation between the physics and math scores? If somebody has done well in physics, does it necessarily mean that she or he will do well in maths, or vice versa? Okay? So how do you, test this? Okay? So to do that, so what you do is you just take the transpose of this matrix, which is just 2 by 3. So in general, it will be n by m. And then you take this product, x transpose x. This is a simple exercise. You can just compute the product. So this will be a 2 by 2 matrix. In general, it will be n by n matrix. And what are the matrix elements? So this is x11 square, x21 square, x31 square. And this is this, and so on. So this is a real symmetric matrix, because the scores are real. Okay. So now what is this object here? So in your sample, this is a very small sample, right? So x11 square plus x21 square plus x31 square. So imagine that, the mean is 0 of this, you have subtracted of the mean. So then this is, if you just divide by overall factor 3, this is just the variance of the physics course, right? There are 3 students. So this is just the variance. Sanjib had already defined variance this morning. So this is just the variance of the physics course. And this diagonal element is just the variance of the maths course, right? x12 square plus x22 square, x32 square. Okay, and what about the off-diagonal element? So this is just x11 times x12 plus x21 times x22 plus x31 times x32. So this is just the covariance, that is, the correlation between physics and maths course, right? Again, you have to divide by overall factor 3, but that goes outside the matrix, so it's not important. And this is just a symmetric counterpart of that. So this is called the, in general, covariance matrix, because it encodes the fluctuations of the scores in your sample. Okay, so the diagonal elements are just variants of different subjects, and the off-diagonal elements give you the correlation between, let's say, physics and math scores. Okay? So if you diagonalize these eigenvalues, this matrix, this covariance matrix, in this case you will get 2 eigenvalues, right? So imagine that, okay, you get 2 eigenvalues, and then you want to know that, okay, I mean, what does it tell us about the correlation between physics and math scores, okay? So imagine that, I'll just give you an example, okay? So imagine that this is the physics course, and this is the math course. So you take your particular sample, right? So let's say you have 3 students. So 3 students, so the first guy has got score x11, x12, so that's just a point in this plane, right? It's called the scatter plot. So let's say this guy got this. So in your one particular sample, you might get suppose you get something like this. So this is student number 1. So this is x coordinate is the physics score, and y coordinate is the math score. This is, let's say, student number 2, physics score, math score. Sorry, physics course, math score. This is number 2, and maybe number 3 is here. Okay, again, physics and math scores. So this scatter plot gives you 3 points like this. Now, if you stare at it, I mean, if I ask you, what do you think? I mean, are the maths and physics scores are strongly correlated or not? You will say yes, right? I mean, it almost looks like they are in a line, right? So that means if physics score is big, math score is also big, okay? So if you are in this situation, then you see immediately from your picture that they are very strongly correlated. On the other hand, you know, if you have scores like this, you can't say anything, right? They are totally scattered, okay? So now this, of course, you can figure it out, because if you take this particular sample and if you just calculate the eigenvalues of lambda 1 and lambda 2, if your scores were like this, if you diagonalize, so what does diagonalization mean? Meaning that you just, you know, just rotate your axis, right? So this will be, let's say, lambda 1 eigenvector, and this will be lambda 2 eigenvector. Okay. So what this situation, if your sample was like that, this particular scatter plot would indicate that there's a lot of fluctuation. See, once you diagonalize, you get a diagonal matrix, right? So lambda 1, lambda 2, 0, 0. So this is like the fluctuations, because overall covariance matrix, and so this is like the fluctuations in direction 1, and this is fluctuations in the direction 2. So if it was like that, you see there's a lot of fluctuation in direction 1, whereas there's hardly any fluctuation in direction 2. So this means that in such a particular sample, if you diagonalize, you must find lambda 1 much bigger than lambda 2. Whereas here, if your sample was like that, if you again diagonalize, you will get, you know, you see this is lambda 1, lambda 2, perpendicular direction. So both sides there is a lot of scattering. So basically in this case, lambda 1 probably is of the order of lambda 2. Okay, so you cannot say much. So the eigenvalues tell you something about the, you know, the fluctuations, and so you want to know that. So, for example, this is at the heart of what is called the principal component analysis, which is one of the main, you know, tool to analyze the big data, which is these days is a big hot subject, if you like. So what does principal component analysis mean? So it's called PCA. So PCA says that, you know, typically, you know, if you're in a situation like this, when one of the eigenvalue is, let's say, okay, in this simple example, you have 2 eigenvalues. In general, if your data is complex, you'll have n eigenvalues. So if one of the eigenvalues is much bigger than the other eigenvalues, okay, that means they're all lined up in that direction. So then, you know, you can basically ignore, the fluctuation. You want to reduce your data, right? Your big data, you want to reduce it. So what you can do is you can throw away all the eigenvalues, eigenvectors in the perpendicular direction and keep only this principal component. That's the sort of meaning of principal component analysis. So what people do in big data analysis, so they have this data, they construct a covariance matrix, look at the eigenvalues, and then they just keep the principal component and throw away all the other guys, okay? So of course this is going to be good approximation if you are in this situation. If you are in this situation, it's not going to be good approximation. But this is the main way to reduce data, big data essentially. Okay, so this is a very important application that which sort of goes back to this Wishart in 1928. Anyway, coming back to our problem now. Okay, so I diagonalize my sample and I get these two eigenvalues, and I have to by looking at these pictures, I can decide whether they are correlated or not. Now the thing is that even so now you are in a given sample, right? So you can look at the eigenvalues and eigenvectors, but then you can say that, imagine that there was really no correlation between them. They are completely independent, IID variables, okay? Imagine that these guys, they are totally independent of each other, okay? So in that case, this matrix, these elements are also random variables, okay? They are correlated, of course, but here they are independent. So this guy, if I look at it, even for completely uncorrelated variables, it has some structure and I can get the eigenvalues and eigenvectors, okay? So even when there is no correlation, there is still some structure in the eigenvalues. And so therefore, if I want to really, in my given experiment, given sample, I want to sort of compare it with the case when there is no correlation, okay? So this is what statisticians call null model, okay? This is something to contrast, basically. So first, what you should do is to figure out what is the eigenvalue and eigenvector structure for a completely uncorrelated scores, okay? So you have that. And then, when you do your new experiment in your class, you can compare the new eigenvalues with this completely random model, okay? So and use that as a null model to decide whether your particular sample, whether the scores are correlated or not, okay? So therefore, what Wishart did was to introduce random covariance matrix as a null model for principal component analysis, okay? So this is the original motivation of random matrix theory came in. So he didn't solve anything. He just said that, it will be interesting as a null model to study the case when the matrix entries are completely uncorrelated, and then what can you tell me about the eigenvalues and eigenvectors of such matrices, okay? So this was Wishart in 1928, and if we put make the clock forward, then in physics, random matrix theory was essentially introduced by Wigner, and amongst his many contributions, but this was one of the principal contributions for which he got Nobel Prize. So what Wigner was interested was in nuclear physics. So he wrote his famous papers in random matrix theory around the 1940s. I don't know which year was this. And but I just wanted to show you this picture here. That so what you see here is a graph. So if you go to an experimentalist, nuclear experiment spectroscopy, they tell you the eigenvalues, the spectrum. So what I'm plotting here is just the energy levels of a nucleus. So you have, let's say, energy at E1, you have an energy at E2, E3, maybe E4, E5, etc. Okay? So just the energy levels, this is the direction of energy. Okay? So let's say this is 1000 millivolt, this is, 2000 millivolt, and so on. So nuclear experimentalists can give you these energy levels. And so what he was interested in, and they can measure the distribution of the spacing between these energy levels, successive energy levels, okay? And you can actually scale it by the mean distance between them. And so this is the plot that you see. If you plot them, you will see that somehow the spacing distribution goes to 0 as x goes to 0, and it has a typical curve like that, okay? So Wigner was interested in finding a theory for this curve. I will show you pictures in a minute. But so historically, so then, so he was giving this talk somewhere in I don't know where was this conference. So it's a conference on neutron spectroscopy. And so the chairman of this conference was this guy, Heavens. And so Wigner says in his talk that then, as I mentioned, and this was known a long time ago by Wishart, and then he talks about the eigenvalues of a random matrix, okay? And then, at the end of this discussion session, so this guy, Heavens, asked him, where does one find about a Wishart distribution? So he said, what does one find out about Wishart distribution? So Wigner replies, a Wishart distribution is given in S.S. Wilkes' book about statistics, and I found it just by accident. Okay. So accidents happen in science, and this is very important, such accidents, because you see, this is already demonstrates the power of interdisciplinarity in science. I mean, you can work in very different subjects, but there is always, science always tells us something common between different developments, okay? And it was extremely thanks to this accident that Wigner could essentially solve nuclear physics problem, and so and in fact, I mean, the subject is still living because of Wigner, and I'll come to that in a minute. Okay, so what was, as I said, what was the problem that Wigner was interested in? So imagine that you have a heavy nuclei like uranium-238 or thorium-232. So this is just a schematic picture of the atom, nucleus. So you have inside the nucleus, you have neutrons, protons, and so on, okay? So, as I said, the experimentalists can measure the spectrum. So this is the energy. So so what does spectrum mean? So it simply means that whatever the Hamiltonian is here, it's a many-body complicated Hamiltonian. If you solve the Schrodinger equation and find out the eigenvalues, so they will be given by this. Okay? So of course there will be real eigenvalues. So this is for uranium and this is for thorium. Okay, so they look different, so who cares? Okay, but then Wigner, when he was talking to his experimentalist friend, he sort of realized something, that even though the details of the spectrum look very different from each other, but you see that if you somehow, the statistics, at the statistical fluctuations of these, there could be some similarity between them, meaning that so what he suggested to his experimentalist friend is to look at the spacing between, just nearest neighbor energy levels, and of course you have to, scale it by the mean distance. Okay, so that means you just look at the, let's say you look at this E5 minus E4, and then E4 minus E3, all these spacings, okay? So these are delta, let's call it, okay. So delta 1 is E2 minus E1, delta 2 is E3 minus E2, etc. Okay. So you have all these deltas, and then you can actually go and draw a histogram of these deltas, right? So there'll be a histogram of these deltas. And what you should do is to scale it, so there will be average delta. Okay. So if you scale it, so then what would you expect is, something of this, some scaling function like this, some p tilde of, let me call this p tilde, and this is p, delta over delta, average. Okay. So you just divide by the average spacing so that the mean spacing is of order 1. If I want to compare between uranium and thorium, the mean spacing of uranium is going to be quite different from thorium. So if I want to compare between them, if I want to do some scaling, then I should divide by the mean spacing. And if you do divide by the mean spacing, you get a function p of x. Okay? And then if you plot for uranium and thorium, then you see that they both, fall onto the same curve, and this is this curve, p of x versus x. Okay? So I didn't show you the experimental data, but you can find out any standard book that uranium, thorium, they all fall into the same curve. So there's a universal function, scaling function, that describes the spacing distribution between different atoms, even though the details are very different. Because you see that, So then Wigner says, told his friends that, look, I mean, if you guys try to find out this function, it's a nightmare because you don't even know what is the Hamiltonian of uranium, right? I mean, you have neutrons, protons, there are all kinds of interactions, God knows what there is, okay. You don't even know the Hamiltonian, and then you want to solve the Schrodinger equation for this Hamiltonian, right? So it's a many-body Hamiltonian, and you want to solve the many-body wave function to get the energy levels, okay? This is a formidable task. I don't even know what the Hamiltonian means, and I don't know how to generally solve the Schrodinger equation. So to get the exact spectrum is a nightmare. So, but he says that, look, I mean, you don't need to get the exact spectrum. If you are interested only in the sort of universal scaling function, there must be some other simpler theory, right? So what he says, what he thought is that maybe what happens here is that the Hamiltonian is so complicated. So Hamiltonian, any Hamiltonian, say, if you write in any basis, it'll be an n by n matrix, right? So he says, okay, your Hamiltonian is very complex. It's a complex n by n matrix. You don't even know what this is. So why don't you just take the elements to be completely random and see what it gives? So you take your Hamiltonian, which is very complicated. You don't know anything about it. You just know that it's a symmetric, it has to be Hermitian and so on. But so why don't you just compare with a completely random Hermitian matrix and look at the eigenvalues of that matrix, and maybe for that matrix you can compute this, and then check your experimental result with that prediction. And amazingly, it worked. It worked beautifully. That okay, these days you can compute exactly this function for n by n complex Hermitian matrices, but Wigner didn't know how to compute that. He actually did it just for 2 by 2 matrix. 2 by 2 he could do it by hand, but even 2 by 2 and n by n didn't differ that much. And it really worked very well. So it's amazing. So this was the first success of random matrix theory, that somehow, so the main thing that you learn from this is that if your system has a matrix description like a nuclei has, and if it is too complex, then maybe something simpler happens. When it's too complex, you just you close your eyes and replace it by a completely random matrix and see what it gives. I mean, it's not guaranteed to work all the time. We don't know if it works all the time. But chances are that it might work. Okay, so in absence of any other theory, this is the best theory that you can have, right? And so this is the sort of Wigner's dogma that is, no matter how complicated your system is, if the system is large and sufficiently complex, that somehow there is a randomization which occurs and which leads to a much simpler description in terms of a completely random matrix. Okay, so this is the sort of central sort of dogma of random matrix theory. And so after that, a lot of people worked on it, Dyson, Godha, Mehta, and many other people, and it's still going on very much. And in fact, because of this central thing that goes much beyond nuclear physics, I mean, random matrix theory now has many, many applications. Let me just show you some list here. So as I said, it started with nuclear physics, and then quantum chaos, disorder and localization, I don't know, these are QCD, string theory, gauge theory, matrix models, cold atoms, which I'll talk about in a minute. This is in physics. So all these problems, you can apply random matrix theory quite successfully. In mathematics, you have the Riemann zeta function in number theory, then determinantal point process, about which I'll talk about quite a lot in these lectures, integrable systems. In statistics, I already talked about principal component analysis, data compression, and this data reduction I told you about. Data compression is very important these days, because when you have a complicated data, you want to send it by your computer, you have to compress the data. And again, principal component analysis is very important there. You want to reduce, when you do your zzip in your file, this is exactly what you do. You compress your data somehow, okay? And then, information theory, signal processing, wireless communications, cell phone that you use. Again, there's a kind of matrix description. I mean, all the people are trying to call, and then the calls are being, I'll come back to that, rerouted to other guys. And so essentially there's an input vector, there's an output vector, and there's a matrix connecting them. And if you don't know anything about them, then again, you can close your eyes and just replace it by a random matrix, okay? In biology and economics and finance, biology, think Joachim is going to, he's not going to talk about random matrix, but there is also random matrix, quite a large applications. And you can find many of this in these modern applications in this book, which appeared in 2011. So let me just, I'm not going to the details of all these things. I mean, I'll mostly focus later on cold atoms, and I'll develop the theory of random matrices using these cold atom things, because that's something that we have been working on quite a lot these days. But let me just, just tell you a little bit about, few things like quantum chaos, for example. Yes? Yeah.
So the Hamiltonian is written.
Hamiltonian is, I don't even know the Hamiltonian.
Exactly. So how does it work?
How does it know? You don't know whether it works. That's what I'm trying to tell you. You have to try. You don't have any other theory. If you come up with a better theory, I'm willing to buy it. Okay. But you don't have any theory. So what Wigner said, that in that case, just replace it by random matrix and see what happens. Okay. And amazingly, it works. Okay. Because as I said, the basic, rationale is that when something is very, very complex, somehow there is a randomization which works at the end. Okay. So you'll see, completely disparate subjects, random matrix theory appears there. So just let me show you this, tell you about this example of quantum chaos. Again, today I'm not going to giving to any details. This is just overview talk. So details, if you have any detailed question, you have to wait for the next lecture, okay? So I just told you what the problem is, and I'm just telling you its applications and a little bit historical perspective. Okay, so quantum chaos, again, without going into the detail. So everybody, or not everybody, I don't know. How many people here know about classical chaos? You've read something about it at least, right? Yes? Okay, at least some of you know. So chaos means what? Okay, see, if I just summarize, chaos in classical chaos in a simple example is the following. So simplest way to characterize classical chaos is, imagine that you have a, some particle which is moving according to Newton's laws, okay? So, for example, suppose I take a rectangle. I have one just single particle, and I just start this particle with some, initial velocity. And then this particle moves with this velocity, Newton's law, so it moves with a constant velocity, goes like this, it gets reflected there, goes this way, gets reflected, goes that way. And so on. So this is the trajectory, classical trajectory of the particle, right? So now if I give you another particle, so this is particle number 1, and if I give you a second particle, and suppose I say that initial condition differs only very slightly. So you just go, slightly epsilon distance from here, and also in the velocity or maybe the same velocity, or just put a slight difference in the initial condition, okay? And then again, if you follow the trajectory with a slight initial condition, but the equation of motion is exactly same for these two, right? So you will find that the second trajectory remains very close to the first trajectory, always, at all times, as long as you are in the rectangle. The trajectories, they stay closer together, okay? So, in other words, x1, okay, in some notation, basically, x1t minus x2t, the distance between these two trajectories, it stays of order 1, basically. It doesn't increase with time. Okay? So you make a slight change in the initial condition, and you ask at a later time t, do they differ very much? The answer is no, if they are in the rectangle. Okay? But now you do a little change in your problem. You just round these corners. Okay? So such an object is called rectangular billiard, like a billiard table. Now you do the same experiment. You take the first guy, one trajectory, and you look at the second trajectory, starting very close to the first trajectory. Okay? But now, you will see after many, many reflections, after a long time t, that their difference no longer stays bounded, but it increases exponentially with time, with some exponent, let's call it. Okay. Lambda L is usually called the Lyapunov exponent. Okay? So this is the definite characteristic signature of chaos. Chaos means that a Lyapunov exponent which is positive. Okay? That means if you make a slight change in the initial condition, then the trajectories diverge from one another. Okay? So this is the classical chaos, essentially. Okay? So essentially, basically because of the rounding of the corners, so when the two guys come closer here, you know, they start diverging from each other, going away from each other, and this thing expands in time. Okay? So now, you can ask, what is quantum chaos? So classically, you have a prescription to detect chaos, right? So you just start these two trajectories together and see if they go away from each other or not. If they don't, if they stay together, it's a normal system, not non-chaotic system, regular system. But if they diverge, then it's a chaotic system. Now, quantum mechanically, I don't have the concept of trajectories, right? Quantum mechanics only tells me that, okay, I have a single particle inside this geometry, rectangle or billiard. I have a single particle, which is a free particle, and I just want to solve the Schrodinger equation inside this boundary domain with appropriate boundary conditions, which you can take to be Dirichlet condition, that psi is equal to 0 on the boundary. Okay? So how do I know? I mean, classically, you see that there's a rectangle and there's a billiard. You know, slight change of geometry makes the system chaotic, from regular to chaotic. If I do the same thing, you know, if I take a rectangle and solve Schrodinger equation, and then I take the billiard and again solve Schrodinger equation, what difference do I see? Okay. So how do I know whether this system is quantum mechanically chaotic or not? Okay. So in fact, so what people did is to look at the spectrum again, that is, look at the energy eigenvalues. Okay. You solve Schrodinger equation and look at the energy eigenvalues, and you look at the separation, precisely this delta I defined, you know, the separation between nearest neighbor eigenvalues. And you want to just look at this delta. Okay. So what happens is that if you take the rectangle, for which you know that classically the system is regular, so quantum mechanically, you find that this is just a Poisson distribution. So take any regular geometry where you know that the classical system is non-chaotic, corresponding quantum mechanical problem, the signature is in the spectrum, you find it's always Poisson exponentially distributed spectrum. Okay? So that means if you plot P of delta versus delta, it's just an exponential distribution. But if you do solve the same problem in a billiard, which of course you cannot solve it exactly, but you can do it numerically, then you see this is rectangle. This is called the integrable system because you can solve the Schrodinger equation exactly in this case. But for the billiard, you can do it numerically only. And you find that this guy roughly does exactly like what we saw in the Wigner distribution of this type, okay? So it's a function which goes like this. In fact, it turns out that this is exactly same again as the eigenvalues spacing distribution of a random matrix, Gaussian random matrix, okay? So again, I mean, you don't see here where is the matrix, where is the random, again, the rationale is that, this problem, when it's a billiard, you cannot solve the Schrodinger equation because it's a very complicated problem, okay? But somehow, the boundary condition here makes the effective Hamiltonian kind of a random Hamiltonian. And if you look at the spectrum, it looks like the that of the random matrix. Okay, so this fact, it was all seen numerically, and then now it has been verified in many different systems, and this is taken as a signature of quantum chaos. Okay, so this is called Bohigas-Giannoni-Schmidt conjecture. Or BGS conjecture. So what this conjecture says is that if your system is classically regular, okay, then quantum mechanically, you will find the spectrum to have a exponential distribution. This is also sometimes called the Berry-Keating conjecture, the first one. Whereas BGS conjecture says that if your system is classically chaotic, like in billiard, then quantum mechanically, you always get the random Gaussian matrix spectrum. Okay. So this is sort of another the whole subject of quantum chaos then essentially developed out of the random matrix theory. I mean, just wanted to show you this example. Okay. Yeah. No, you just solve the Schrodinger equation.
Yeah, but this is equation.
Yes, but no, distribution. You just draw the histogram. You go to very high energy level, okay, and draw a histogram. You go along, take a big window, okay, take L window size. Look at the histogram, okay? And then you take the, just slide this window. And you can plot the distribution of P of delta, right? By distribution, I mean, this is, you have these big points, many points like that, right? You take here a big window, and you look at these guys, you find out how many spacings are there of length 1, how many spacings of length 2, how many spacings of length 3, etc.
Eigenvalues themselves are fixed.
Yeah, eigenvalues. This is a fixed point line. Yeah, I'm just sampling the distance between the eigenvalues. Okay, and then I can plot a distribution by taking a big window size and then sliding the window size, from different subsamples basically. Okay. Yes. Chaos. Chaos means essentially that it's not regular, right? So it's because of this billiard structure, it gets. Actually it satisfies Newton's equation, but the thing is it gets chaotic, meaning that it has multiple scattering, so much of them that you can't really follow the deterministic trajectory basically. Okay. Yes. Quantum mechanically nobody knows. That's something. How do you quantum mechanically we don't have a notion of trajectory, right? So how would I detect quantum chaos? So what these guys are telling you that for that you have to look at the spectrum. If the spectrum looks like the random matrix spectrum, the system is chaotic. That's the conjecture. Yes. Yes, right. There are some measures, but I'm not going to the details of that basically. But all I'm trying to say is that the quantum mechanically, essentially the spectrum. You should look at the spectrum. Quantum chaos theory of quantum chaos says that to detect the signature of chaos, you should look at the spectrum. And if the spectrum looks like that of a random matrix, okay, then you know that this is a chaotic system. That's the conjecture of BGS. Okay. Okay. So this is just one example. Okay. So the second example, just to continue with these examples. Okay. Let me keep this side. I mean, I insist again, this is just a, I mean, I'm not defining in detail yet all the different definitions and everything, just to give you, this is just an overview. I mean, just to tell you that why quantum mechanics, random matrix theory appears in different places. So, again, I will not give you details, but all of you must have heard about Riemann zeta function. This is the famous is defined as by this series. Huh? Yeah. Yes. Well, that depends on what is your dimension of your Hamiltonian, right? No. If you for example, if you take just a Anderson model or lattice model of n sites, okay, I mean, you have to determine what is your state space. I mean, you have to determine what is the Hamiltonian in a certain basis. Okay. Yes. Dimension of the matrix? Yeah, if you have just n particle, okay. So n particle, there will be n by n matrix essentially, right? I've not told you Wigner solved. I mean, Wigner, I mean, basically he conjectured. Wigner conjectured that if you look at the spacing distribution of a completely random Gaussian matrix, that this describes pretty well the scaling distribution of all these nuclear physics problems. Okay? Higher dimensions? See, nobody knows when it, I mean, there's no criteria for random matrix theory to work, okay. There's nobody else to tell you, gives you a criteria, but I mean, the main point is that, in the absence of any theory, this is the first approximation you will try. And the chances are that it might work actually, because, when the system is sufficiently complex, somehow there is some kind of randomization that goes on, okay. This is the main idea. This is the idea you have to keep in mind, okay. Because usually these random matrix problems are not always easy, as we'll see during the lectures that they are quite tough problem actually. So zeta function this is defined for z bigger than 1, and then z less than 1 you can do an analytic continuation. But the famous Riemann hypothesis, which says, okay, zeta function this is the complex z plane, and you look at the zeros of zeta function. In the complex plane. Okay. So there are some trivial zeros on the okay. So this is the z plane. This is 0 here. So there are these poles here at -2, -4, -6, etc. So this is defined for z strictly bigger than 1, and for z less than 1, you have to analytically continue. Okay? So there are some trivial zeros of the zeta function. This is very easy to prove that they, on these negative poles at even integers, is always 0. And the Riemann conjecture, Riemann hypothesis, says that all the non-trivial zeros, they lie on this imaginary axis, vertical axis with real part half. So this is the point at x equal to half, and so all these, so there are infinite number of poles on this line, imaginary axis. It's called the Riemann hypothesis. This is one of the most coveted problem to solve in mathematics. You'll get $1 million immediately if you can prove Riemann hypothesis, Clay Foundation Prize. So many people have tried, and it's still, still open problem. So Riemann conjectured that, or hypothesized, that all the non-trivial zeros, they lie on this single imaginary axis, half plus whatever, something into I. An times I, where An is the location of the nth zero in the vertical axis. And so there are many things, many nice properties of these things are known. And there's a guy called Andrew Odlyzko at Bell Labs. He used to be at Bell Labs. We actually developed a special computer program to find these zeros. And he has the world record. I mean, he has gone up to 17 billion zeros. And they're all still, on the imaginary line. Okay, so there is no exception so far. Okay, so everybody believes that Riemann hypothesis is true, but proving it's very hard. Okay, so while you cannot prove Riemann hypothesis, what people try to do is to, understand again the statistics of these things. Okay, so for example, if you go very high up, okay, along this imaginary axis, and you look at these zeros, and again you look at the spacing between successive zeros. We call it delta 1, delta 2, etc. Okay? And once again, you take a sample, big window, and just draw a histogram of these deltas. And what you find, and there's a lot of work by Keating, Smythe, Montgomery, and many others people. And what people now conjecture is that if you go quite high up and look at the spacing between successive zeros along the vertical axis, I mean, this is not proving Riemann hypothesis. This is just saying that, okay, I mean, assuming that the Riemann hypothesis is true, what can we say about the location of these zeros, these ANs, right? And again, the spacing distribution, it turns out that once you appropriately scale and center, that this is given by the random matrix answer, Gaussian random matrix, GUE. Okay, I didn't define it, so Gaussian random matrices. That means you take a Gaussian, independent Gaussian entries random matrix to find out the eigenvalues, and you look at the spacing distribution between successive eigenvalues, and somehow the zeros of zeta function, their spacing distribution seems to be exactly again given by RMT. So again, you don't see any matrix here, right? It's just somehow, there's no matrix appearance here, but you see somehow indirectly the random matrix appears in these problems. I mean, again, you don't try to even ask me a question that why random matrix, because I don't know, nobody knows, okay? But this is just an observation that random matrix theory seems to appear here. So basically, it's a point process. So you have these points, random points, and again, for some magical reason, that RMT appears again. So this is just to show that RMT appears in many, many different problems. Some of the problems we understand why it appears, but some of the problems we don't know. I mean, and you see the range from gauge theory to the polymer problems to string theory to information theory, all these things. So it's just a huge, vast amount of subjects which somehow have connections to random matrix theory. Okay, so this is the sort of great thing about RMT. Yeah.
What about the distribution of the zeros on this? Are they kind of uniform or?
No, so the thing is that global properties are not the same. Okay, only local properties. I mean, if you look at actually even the people have now computed not just the spacing distribution. If you look at the correlation function, the m-point correlation function, it seems to be identical. Yes. So somehow this point process is behaving like the eigenvalues of a random Gaussian unitary matrix, but nobody can prove it. Okay. So I mean, I'm just telling you this spacing distribution because that's how originally it was found. But now they can actually calculate this joint distribution of these points. Okay, a measure basically numerically, and they are exactly identical to the GUE matrix basically. Okay, so what I'll do is next, and then this is again, as I said, this is an overview talk. So next, I want to just tell you that one recent application, which is this cold atom physics, because this is, I find it quite fascinating. This is a new addition to this list, And so let me just, next half an hour, just tell you a little bit about cold atom physics. So cold atoms. So what is cold atoms? So I mean, all of you have heard about cold atom systems. I mean, this is a very hot area in physics these days due to experimental physics. So as you know, there is a great sort of experimental advance in the cold atom system. So these are basically systems with a optical laser trap, which can confine the particles in a finite region in space, and these experimentalists, they are mostly atomic physicists and optical physicists, so they can actually do a lot of manipulation. Okay, so essentially this system consists of atoms in a confining laser trap. Okay, I'll show you a picture in a minute. So they can fabricate this system in different spatial dimensions, 1, 2, 3, etc. They can tune the interaction between atoms. Okay, they can tune temperature and also the number of atoms. So a lot of variability in these experiments, a controlled variability. I mean, essentially, this subject has got 3 Nobel Prizes in the last 20 years. And the reason is because they can fabricate, essentially you give them any Hamiltonian. See, I mean, if you work on, as a theorist, if you work on a Hamiltonian, there's no guarantee that you will find this Hamiltonian in any condensed matter system. Okay, often you don't find. Okay, but in cold atom system, actually, they can fabricate the Hamiltonian for you. If you give them, okay, you tell them, look, I have a Hamiltonian which is like this. Can you find a system? And the most chances are they will find the system actually which does this. Okay, they can sort of basically manipulate these atoms in a very many different ways. Okay, and in particular, it's essentially quantum simulation, if you like. Yes, if you want to tell it. Now, the important thing is that the interaction between the atoms are also tunable. In particular, they can probe the system even in the non-interacting limit. And this non-interacting limit is actually already quite interesting because even though there is no direct interaction between the atoms in this non-interacting limit, but you still, because these are quantum systems, so quantum statistics play an important role. So for instance, I mean, if you have a bosons, you can have Bose-Einstein condensation, which means that a lot of bosons might condense onto the ground state. Or if you have fermions, which tells you that there is a Pauli exclusion principle, which tells you that 2 fermions cannot sit on the same place, okay, or in the same state. So these constraints give rise to non-trivial spatial correlations between these atoms, even in the absence of interaction, just the quantum effects, quantum statistical effects. Okay, so this has been probed experimentally. Bose-Einstein condensation, of course, was known for a very, very long time. But experimentally, it was observed only in the early 2000s. And similarly for fermions, there are a lot of things you can do. And as Joachim was saying this morning, I want to show you. Okay, so this is the sort of typical common feature of these experiments is that you have a sort of confining trap here, and you have some atoms here. So this is and you have some Hamiltonian. So this is and this trap, what does it do? It breaks the translational invariance, right? So the system is now confined in a region. It cannot go very far because of this external potential, okay, which is trying to push it to the center. And so it's a confined region of space. And you can ask, what are the sort of correlations and, other properties of this many-body system, okay? And yeah, as I said, this morning Joachim mentioned that you can, see atoms in scanning tunneling microscopy. Here you actually see, this is called the Quantum Gas Microscope, which was developed by the Greiner group in Harvard quite recently. And you can actually, these are the images, these blue ones, these white ones, white, blue, whatever. I mean, this is just a 2-dimensional atoms, basically fermions, these lithium-6 atoms. Okay? And they're in a trap, so they're in a confined region, okay? And you can take the images, pictures of atoms like this, and you can actually, for example, you can go into a particular region, you can count how many atoms are there just by counting the pixels and so on, and you can look at their fluctuations. So central question here is that this quantum many-body system, so what can I say about the spatial fluctuations in this system, even in this non-interacting limit? Again, I mean, I want to, I'll come to that maybe later, non-interacting fermions, if you say, most people will say, but this is a trivial problem. Yeah, trivial problem if you want to calculate the spectrum, but if you want to calculate the spatial correlations, is highly non-trivial, okay? In other words, the second quantization is trivial, but the first quantization in quantum mechanics is not so trivial, okay? So the bulk properties of these non-interacting fermions, for instance, okay? So if you are here, you don't see the curvature. So here it's a translational invariance applies, and you can actually solve this system by standard many-body theory like Thomas Fermi approximation or local density approximation. So everything is known in the deep inside the bulk. But when you go near the edge, because as I said, they are confined in a certain region of space, if you go near the edges, because the particles are very few, so the fluctuations are very important, both quantum and thermal fluctuations. So and you cannot apply the bulk translational invariant system. So to describe describe the correlations near the edges of this confined cold atom system, right? What can we say about the edges? In fact, this problem was pointed out almost 20 years, 30 years back by Walter Kohn, who is again a famous chemist, Nobel laureate. In fact, he says that the uniform electron gas, the traditional starting point for density-based many-body theories of inhomogeneous systems, is inappropriate near the electronic edges. Okay, you cannot apply the many-body theory, traditional many-body theory of translational invariant system out here, free fermions, is because of the trap. There are non-trivial correlations and fluctuations which appear at the edges. Okay, so how do we describe these edges? So again, what I want to show you, and this will be, during the lectures, is that indeed these atoms, these fermions in a confining potential, harmonic potential, let's say. So you can actually map these positions of the atoms in the ground state to the exactly again the eigenvalues of a Gaussian unitary matrix, meaning a Gaussian matrix with complex Hermitian matrix eigenvalues, basically, okay, with Gaussian entries. Okay, so the positions of the atoms will behave like the eigenvalues of a random matrix. So once again, the random matrix theory has been extremely useful in understanding the properties of such cold atom systems, and this is a sort of theme of research that we have been working for since last 5 years with several of my collaborators, and you can find a review in a recent review on this subject. But I'll try to develop this as we go along. Okay, so this is the sort of main plan. So what I'll do in the next lecture, since I'll not have enough time today to start, is I'll start with this, and I'll just first try to tell you that what are the possible ensembles of different random matrices. So now we'll go more detailed. This was just an overview thing. And then I want to show you how to compute the joint distribution of eigenvalues starting from the joint distribution of entries. And once we know that it's not always easy task, but some cases we can do, at least for Gaussian entries we can certainly do. And then once we know the joint distribution of entries, then you want to calculate certain observables, like for example the spacing distribution or the distribution of the largest eigenvalue and so on and so forth, or the average density of states. So there are many other interesting observables that you can try to compute the spectral properties of these eigenvalues. Okay, and so this is the sort of plan for the and then on the way, when I develop this theory of how to calculate correlation functions or spacing distribution, etc., I'll just use this language of very basic quantum mechanics. Okay, so hopefully you will see that there are a lot of jargons that are used in the random matrix literature, but you will see it's exactly like solving a simple quantum problem. For instance, the method of orthogonal polynomial is nothing but just doing single particle quantum mechanics. Okay, so it will be very, hopefully it will be very clear as we go along to when we do in detail these things. Okay, so let me just summarize then today's the overall introduction is just so basic problem is clear, right? So you just give me an n by n matrix, and let's say with some symmetries such that the eigenvalues are real, but you can also talk about complex eigenvalues, and there are physical examples which correspond to complex eigenvalues, and then you give me the joint distribution of the entries, and the generic problem is to find the joint distribution of eigenvalues first, and then once, So there are two steps. So given the suppose you give me this. I have given you an example which is the Gaussian, but you can, for example, you can choose the entries to be from uniform distribution or exponential distribution, whatever you like. Okay, I'll tell you more detail about different ensembles of random matrices in next lecture. So given the joint distribution, so our first task is to this is a formidable problem, it's a very difficult problem, and in many cases the answer is not known. Okay, so just to give you one simple example, okay, so first task is to and often we'll see that even though the entries may be independent, like in the Gaussian IID case, the eigenvalues will still be correlated, okay? So which means that the eigenvalue distribution is not going to factorize. So this is as I said, it's a very difficult problem. In fact, for most cases, it's not known, the joint distribution, okay? So, for instance, let me just give you one simple example, okay? So, this is a network problem, random network problem. So suppose you have a graph. Let's say, as a simple example, let's take a graph of three nodes, 1, 2, 3. Okay? And let's say I have some connection like this between 1 and 2 and 1 and 3. Okay? So this is a graph. It can represent whatever, some company with some connections between them, or, some buyers and sellers in finance, and many other things, okay? Cities, different cities. So for any such graph which is given by a set of vertices and a set of edges connecting them, you can construct what is called the adjacency matrix. So adjacency matrix is, so Aij is 1 if I and j have a common edge. And 0 otherwise. For instance, for this graph, this will be a 3 by 3 matrix. So 1, 2, 3, 1, 2, 3. So 1, 1 element, okay, diagonal element you can put it to be 0, or sometimes some people put it to be 1, but okay, let's put it 0. And then between 1 and 2 I have a connection, so I put a 1. And then 1 and 3 I have a connection, so I put a 1. Then 2 and 1 I have a connection, which is 1. 2 and 3 there is no connection, so 0. 3 and 1 there is a connection, 1. And then 3, 2, no connection, 0. Okay. So this is a 3 by 3 adjacency matrix. Okay. And so what you see, adjacency matrix is a sparse graph, sparse matrix, because many eigenvalues are 0, right? I mean, many connections will be 0 because there is no direct link between the nodes. Okay. Now, if you say that, okay, I give you a random graph, meaning that these, some links are there with some probability, and with some probability they are not there. Okay, which means that these guys are going to be now random variables. So link is either there or not there. So it will be Bernoulli variables with some probability. This is called the Erdős-Renyi graph. And I ask you, okay, what are the eigenvalues? What can I say about the eigenvalues of the adjacency matrix? Given the distribution of the Bernoulli distribution of the entries. Okay. So nobody knows what is the joint distribution of the. So again, this will be a symmetric matrix, so there will be n real eigenvalues. And if I ask you what is the joint distribution of this, this is a totally open problem. Okay. So there are very few cases where you can actually, given the joint distribution of entries, you can determine the joint distribution of eigenvalues, and the Gaussian is only one of those rare examples. And I'll mention for which classes of distributions you can actually determine the joint distribution of eigenvalues. So this is the first step of this problem. So some cases, if you are lucky, you might get an exact form for the joint distribution of eigenvalues. But then the next step, this is step 2, is that suppose you know this, and we'll see examples of that, then from that I want to calculate several observables. For example, so this is more like a statistical mechanics problems. Statistical mechanics problem, for example, Ising model, you give me the probability of a spin configurations of different spins, and if I ask you, okay, can you calculate the 2-point correlation function? Okay, 1 and 2 dimension you can do it, 3 dimension nobody knows how to do it. Even though we know the probability of different spin configurations, we cannot calculate correlation functions, right? So knowing the joint distribution is not a guarantee that you can calculate everything explicitly. Okay? So calculate the observables. So observables, for example, let's say largest eigenvalue. So largest eigenvalue is also going to be, so this is exactly the extreme value problem that Sanjib was talking about. Sanjib was talking about when this is factorizes into individual distributions, IID case, right? So this is the independent. And then the calculation of the extreme largest one of them is maximum is very easy, as he showed you directly. Okay, you just have just one integration and you are done. But imagine that you don't have this, but maybe you have, okay, I'll give an example. Okay, so we'll see this, and this is what I mean by correlation: lambda I minus lambda j square. In fact, if you take the Gaussian ensemble, if you take Gaussian entries, complex Hermitian matrix, we'll see later that the joint distribution is given by a product of Gaussians times something called van der Monde square, lambda I minus lambda j. So every pair of eigenvalues, they repel each other because of this presence of this factor. But you see, because of the presence of this factor, they are strongly correlated. Okay, if you did not have this factor, then they would uncorrelate, they will be totally uncorrelated, they will factorize, and in that case, distribution of the largest eigenvalue will be Gumbel, Frechet, or Roybal that Sanjib talked about, or he's going to talk about tomorrow, but he already showed you the example of Gumbel. This will be Gumbel distribution. But because of this guy here, it's not going to be Gumbel, it will be something else. So the strong correlations actually between different random variables make the extreme value problem very hard. And in this particular case, it's known, and we'll see that it's something called the Tracy-Widom distribution, which is again another very famous distribution which has appeared in many, many different problems. So then you can ask, this the number variance, okay? Or, how many eigenvalues are there? Number statistics, full counting statistics. Number statistics, meaning that suppose I take an interval minus L to plus L, or any interval if you like, let's say A to B. If the eigenvalues are real, they are lying on a line, right? And I take an interval A to B, and I ask how many eigenvalues are there, okay? The number. So that's the number, but it fluctuates from one sample to another sample. And I can ask, what can I say about the mean number of eigenvalues, the variance of the number of eigenvalues, or higher cumulants, and so on, okay? So this is called the full counting statistics. Then I mentioned already that there is a spacing distribution, spacing between successive eigenvalues. And there are many other, such observables. So this is a more technical problem. I mean, the joint distribution exactly. Okay, we'll see how to derive this at least later. But knowing this, to compute these things is not always easy, okay? And so this is a whole subject by itself. So this is more akin to statistical mechanics problems. And so there is this step 1 and step 2. Sometimes, this is easier and this is more difficult. Sometimes, this is, much more difficult to do. And then, I mean, if you don't know the joint distribution, you can't even compute many of these things. So this is the sort of, and then, the correlations between eigenvalues, local correlations, local and global scale. Correlation function. So these are the different observables that we want to compute, starting from the joint distribution. So basically, this is the 2-step I want to do. At least I want to first, introduce you to different ensembles. That's the sort of flowchart, different ensembles, and then we'll see under what conditions can you determine the joint distribution. I mean, in some cases, when are you able to calculate the joint distribution? And then, after computing the joint distribution, then from that, what can we do to compute these different observables? Okay, so that's the sort of the main program, and I'll do this. We'll see that this is sort of also very closely related to this quantum problem of non-interacting fermions in a harmonic trap, and so using just very basic methods of quantum mechanics, we can do many of these computations. Okay, so that is the sort of goal of the next few lectures. Okay, so thank you very much.